All right, thank you for that introduction. So I'm going to talk a little bit about open set recognition in the context of machine learning. So step number one, what is open set recognition? This week we've heard a lot about machine learning tasks, and we've heard this term classification thrown around quite a bit. And the classification setting is usually a classic closed set problem. So here's an example from computer vision. Some classes from the Places2 data set, which is drawn from the ImageNet 2016 challenge. The idea here is at training time, you get a bunch of different examples from these particular labeled classes. And again, they're places, so airfield, campsite, gas station, mountain, water park, etc. And you're going to train your classifier to distinguish between these different classes. And then at inference time, you're going to get examples from these classes again, but different examples, not examples from the training set. And the good news is you don't have to worry about anything that doesn't come from outside of these classes. So the question then is, how useful is classification for real-world tasks? Because out there in the real world, we have to worry about everything. So one can imagine an application for, say, autonomous driving, where we have to detect all of the cars in a scene while rejecting the trees, the signs, the telephone poles, basically everything else in the world. And this is extremely challenging because there is so much variance in visual appearance. Even if we could figure out what all of the objects are in the world, it would still be extremely challenging to build a classifier that captures all of them. Another vexing problem, new objects do appear. For instance, this didn't exist maybe 15 years ago, right? No one would know what this thing is. But now, of course, we know it's a phone that we carry around, a smartphone. So what are we going to do in the midst of all of this unknown? We have to develop some new models in machine learning to be able to reject these things that we're going to see at inference time that we don't get the luxury of seeing at training time. Okay, so we can define open set recognition as the following. Incomplete knowledge of the world is present at training time, and unknown classes can be submitted to an algorithm during its operation. And again, there's so many interesting problems where this is the true evaluation regime compared to something like stock classification in machine learning. So at this point, I'd like to invoke some words from my buddy Don Rumsfeld, who famously started a speech with "there are known knowns," and then went on to talk about things that are known, things that are unknown, but we know we don't know these things, and then the very problematic category of unknown unknowns. And of course, he was talking about national security issues on the eve of the Iraq War, and he was widely panned at the time for making these statements, which in retrospect are pretty smart. Because there are things that we don't know that we don't know. And those are the most problematic things when it comes to something like building a model. So if we recast Rumsfeld's words for machine learning, we end up with the following taxonomy. We have known classes, and these are going to be the classes with distinctly labeled positive training examples. And they could also serve as negative examples for other known classes. No big deal. Again, that's what we usually have when we're doing supervised machine learning. We may also have some known unknown classes as well. These would be labeled negative examples, not necessarily grouped into meaningful categories. If you're familiar with computer vision, you've probably seen this type of data as well. If you're training something like a detector, maybe a face detector, a pedestrian detector, etc., you're going to sample a bunch of irrelevant patches from scenes that aren't from the target object. And you're just going to throw them into the training regime, and hopefully they're useful negatives. And then we come to the thing that the machine learning community has ignored for quite a long time, the unknown unknowns. These are these classes that are unseen at training, and we have to deal with them in operation. So to make this a little bit more concrete, let's consider a bunch of different computer vision problems categorized by openness. So here on the left of the slide, we see the closed set regime. Again, familiar classification where maybe we get 3 different classes and we have to separate examples from these classes, and all of the training and testing samples are going to come from those known classes. Then we can move on to something like face verification. This isn't full-blown scene understanding, or it's a very targeted face recognition type of application, but it's a little bit more open because there is a possibility in authentication-driven face recognition where an imposter could sit down in front of the computer and say that they are me, right? Or maybe they say they're Halle Berry, and the computer has to figure out whether or not this claim of identity is true. And so the number of imposters could be the entire population of the Earth. We have interesting generative models that can synthesize faces these days. Perhaps that set is practically speaking infinite, but still limited to just one object category, the human face. We can continue on thinking about detection, which I think a lot of people in computer vision do treat in some sense as a form of open set recognition. Here we're going to have one class that we're trying to recognize, for instance, pedestrians here, and then everything else in the world is a negative. So it's a pretty large negative set. And there are lots of different benchmarks in computer vision that have been designed to evaluate detection. The troubling thing about a lot of those benchmarks is that the negative samples are all sampled from the same distribution because they're all coming from the same data set, which is often acquired from the same exact camera, same sensor. So we definitely want more variation if we're trying to treat this as a real world problem. And then finally, we have what we'll call full-blown open set recognition, where we have multiple known classes and many unknown classes that we have to deal with. OK, so now let's think about this as a statistical learning problem and try to figure out a formulation in a formal sense that could help us address this problem, because it's tough. And so the first thing we would do is probably go back to the literature and try to figure out, has somebody figured this out in the past? Maybe there's something in the very familiar formulations that we can use to solve this problem. So something that would come to mind immediately is probably this notion of ideal risk, which was posed by Vapnik back in the 1960s. Ideal risk is simply integrating over the output of a loss function, which is going to assign penalties for misclassification. Given the training data where we have training samples X, right, the extracted feature information, and then their corresponding labels Y, and some learned recognition function, multiplied by the joint distribution of those feature vectors and those labels. The trouble with this formulation is that it's undefined for open set recognition. Why is that the case? Well, we don't have all of the training points from all of the classes we could possibly see. So this doesn't really help us minimize the risk of the unknown. It only helps us minimize the risk of the known. So what does that mean for something like a support vector machine, right? A very common linear classifier. It means that we face a risk of open space. So imagine I have the following setting. I'm trying to train a classifier that's positively classifying images of dogs, and then everything else that's submitted to this classifier should be negative. So we'll have to sample some sort of negative set, and I'll choose, it looks like frogs here, and birds, and some owls. And I'll learn my maximum margin classifier. I'll get a nice decision boundary. And for those classes, it works just fine. So then what happens when I have a new class, perhaps class raccoon? I extract some features from this class. I throw those feature vectors into the decision machine. And lo and behold, I get an answer. Right? Ideally, this should be undefined, right? Because we never gave the machine any examples of raccoons. But because we have half spaces in this classifier, and because we have one decision boundary, it will happily give us an answer for any feature vector. So in this case, the raccoon ended up on the positive side of this classifier. And notice that it's very far from the positive support of the training data. So what is going on here? Well, it turns out all that open space is extremely risky. Because the feature space is broad, we can have feature vectors appear on either side of the decision boundary, especially feature vectors that aren't drawn from these known classes. So the problem we'd like to solve is this, essentially. If I have something that's way out in space where nothing really should have any label, what can I do? How can I stop that? So turning to a really simple benchmark, I think probably everybody in this room is familiar with the MNIST benchmark in machine learning. It's a toy data set of just handwritten digits, 0 through 9. And the idea here is if you have a new algorithm, ideally it should work on MNIST. If it doesn't work on MNIST, something is very, very wrong. Virtually all useful algorithms are at ceiling on this particular data set. So the idea, again, is I see a new instance of the character 0 or 1 or 2 or 3, and whatever algorithm I have doing classification should tell me that it's the 0, 1, 2, or 3, or however, whatever digit I'm looking at. And so we can see if we're doing normal closed set operation, which is how the data set was designed, things like one versus rest SVMs are basically perfect. There are a few very, very difficult digits within the data set that humans have trouble recognizing. That's why the performance isn't exactly perfect, but it's basically at ceiling. And so again, this is a completely unsurprising, perfectly expected result. But an interesting finding when we started to first dig into open set recognition, we asked the question, what if we train classifiers that only got to see digits, say, 0 through 5, and then at testing time, we started to bring in these other digits. We know that this data set is so dead easy, maybe it wouldn't make a big difference if we just estimated some empirical threshold and then use the one versus rest SVM again. It turns out that that wasn't the case. As we continued to open the problem to expand the unknowns, the performance dropped. And so we had to turn to some new solutions that would more gracefully decline as the problem became more open. But still, when we published this result, it was surprising to many people because they assumed even in open set operation, MNIST is so trivial, it should be easy, regardless of what we're doing in terms of knowns and unknowns. But that's not the case. So flash forward a few more years, and we're in the realm of deep learning. And of course, deep learning is addressing not necessarily classification explicitly, but the feature space. So maybe there's something in the feature realm that can help us with this problem. So of course, in computer vision, features are addressing this issue where we can't just take the raw data because there's too much ambiguity, there's too much noise. And if we look at, say, the raw pixel space, there's going to be entanglement. So we can imagine a trivial face recognition task where we have two individuals, Joe and Sam, who we'd like to recognize. We can't do this with pixels. So in classic computer vision, we would use features which, drawing an analogy to the human visual cortex, are approximately V1-like in nature, meaning that these features extract oriented edges. These would be feature descriptors like SIFT and HOG and SURF, everything we used before 2012 or so. And this is better. We get some separation between, say, our two identities. And it works in some capacity, but anybody who remembers that era of computer vision knows it wasn't that great. It was hard to make a useful application. So flash forward even further to the era of deep learning. Now we have really great feature representations which can pull apart identities, and we can use a simple linear discriminant to distinguish between them. So then the question is, does deep learning in a feature learning sense address open set recognition? Well, the answer is no. We have the same exact problem we had when we were stuck in SVM land. Unknown individuals can fall on either side of that linear discriminant. In the feature space, it doesn't really matter. So we're still stuck. But we can think about the design of neural networks and then look towards the readout. Right? This is the part of the network where we do classification. Maybe that's what we should look at and see if we can make any minor tweaks to any of the standard readouts that we use in deep learning. So the first thing we would think about is Softmax, of course. And here is the formula for Softmax. And notice that it's a summation over all of the classes. Well, that's not very helpful for open set recognition because I don't know what all the classes are. All right, so that one's out. What about linear SVM? Well, we know that one already doesn't work because we've explained it has a half space problem as well. We need to know the positive or negative samples, all of them if we're going to do this as our readout. So what about cosine similarity? This one is a little bit more intriguing because it has no hard notion of training samples, right? It's just a similarity measure. And if we're making decisions using it, we apply some threshold. And the trouble with these thresholds is that they're empirically determined, which means we are stuck with the data that we have at training time to build the decision boundary using something like cosine similarity. So that doesn't help us either. So we went back to the drawing board and tried to develop a series of algorithms that incrementally chipped away at some of the aspects of this problem. So the first take here is solving that half space problem that linear SVM has. So let's develop a little bit of theory here that can help us. Remember I mentioned earlier that ideal risk doesn't really help us understand this problem because it only assumes that we have data points which we know about. So now we need something that is able to express this open space risk where we have this vast space of unknowns. And so we can define open space risk as the relative measure of open space to the full space. What does that mean? All right, so we have this expression here. On the top, we have open space, and that's basically all of the space where there is no support from the training data. That's that vast expanse of nothingness that is still part of the valid feature space, but is so far away from the known training data that we shouldn't have any labels there. And then on the bottom of this fraction here, we have all of the space, which is open space plus the positive training examples, which of course exist in the space. And so if we calculate this fraction, we can figure out how risky a particular solution is in a fairly straightforward way. Yes? Is the denominator just 1? Not necessarily, right? Depending on whether or not I've bounded the space. Right? So if I have the full space and then I apply bounds, depending on my positive training data and the open space, it's not necessarily just 1. Okay, so open set recognition, the preliminaries. The space of positive class data would be P. The space of other known class data we're going to call K. The positive training data we'll say is V hat, and that's going to be drawn from P. The negative training data is K hat, and that's going to be drawn from K. And then we're going to have some unknown negatives appearing in testing, which we'll call U. And this is kind of confusing because where do those unknowns come from if we're doing evaluation? Well, we have to obviously simulate them. So that would be some kind of held out set of data, which we bring in later. And then testing data is just going to be the union of all of those things. And then we'll always assume that the problem openness is greater than 0. So the open set recognition problem, here's what we want to do. Here's the new formulation. So we're going to minimize open set risk. So we're going to have some open space risk associated with those unknown samples. And then we're also going to have on the other side of this, an empirical risk function, which is basically just how we would calculate error in a normal sense, right, if we're doing classification. And then we can also have some regularization constant lambda. And so we're going to combine then the risks from both, right, what we can observe versus what we can estimate as being risky because of the open space issue. And then if we need some regularization, we can add that as well. So here is the algorithm in a nutshell. It's just a simple slab model. So what we're going to do is have our same setup like we did before with the SVM. We have our positive data here, which again is dogs. We've got some sampled negatives, and we have our problematic raccoon out here in open space. So here's the original decision boundary. We're going to call that slab alpha. And then on the other side of the positive data, we're going to define another slab, which is called omega. And when we solve this, it's going to be really simple, because what we're going to do is train something like a linear SVM as we ordinarily would, and then we're going to do a post hoc score analysis, applying these two thresholds to make our decision. And we can solve an interesting optimization problem that'll let us generalize or specialize as necessary. So what we'll do first is define the base one versus set machine, which is what this algorithm is called, which will, figure out based on that positive training data where to initialize these slabs. Then we're going to refer to our known negatives to figure out, do we need to generalize, which of course is a big struggle when it comes to machine learning in general, because we know we're going to see new instances of known classes, and we have to go beyond our experience to recognize them in many cases, so we can't have very tight bounds around that training data. And then we can also specialize assuming that we have a messy feature space, right, and we're not going to be able to have perfect separation, which again, depending on how strong our features are, may be the case. Even with learned feature representations, we often have some messy mixing in the feature space. So in that case, we may want to push these back. So then the question is, how do you do this? Again, we can use these known negative points as reference, and we can move out towards, say, the nearest negative point. Maybe we'll go halfway if we're doing some sort of margin-based separation. Again, we can treat these as hyperparameters depending on empirical estimation in our validation set. Okay, so does this work? Does this actually help us in an open set case? So we could consider a setting like open set object recognition. We can do a cross data set methodology where we're going to take some training data, in this case from a data set from computer vision called Caltech 256, and we're going to pick a bunch of known classes, and then we're going to go to a testing set, which is going to be Caltech 256 plus ImageNet, another much larger, more difficult data set, where we're going to draw known classes, which are consistent with the classes we saw at training time, plus a whole bunch of unknown classes beyond what we had at training time. And then we'll define this open universe of 88 classes where we have, for each classification machine, one positive class, n training classes, 87 negative testing classes, and that's going to be a total of just over 500,000 images. And if we look at this on a class-by-class basis, so the blue curve is our binary one versus set machine with a linear kernel. And then the red curve is just a binary SVM with a linear kernel, so not having this lab model. We can see in all of these cases that we are having some effect by bounding the space with that backplane in the new formulation. And then we can also have a bunch of other alternatives. We could consider maybe a one-class SVM, which was originally designed for problems like open set recognition, but if you've ever used it, it doesn't work very well. But you can play the same game with that as well, because again, this is a post hoc score analysis procedure. And the results are sort of not as good. In some cases, it's better. In some, it's basically the same. But again, with such a weak model, it's not ideal. We could also look at another task like open set face verification, looking at a data set called labeled faces in the wild, where we have genuine face pairs and also imposter face pairs. We can define, say, a gallery of 12 people with at least 50 images, and then large number of imposters, in this case 82 other people. In this case, we'll have about 1,300 test images across all classes. And then we can pick a feature representation. Here we've used pre-deep learning features, LBP and also Gabor wavelets. And we see the same effect when we apply this classifier in this feature space and in this problem. The one versus set machine is superior in both feature representations compared to just using normal SVM. Okay, so that's one way to do it, but it's not great. Because if you notice what we're doing, we're just adding that backplane, and that doesn't really help us put bounds around all of the positive training data, right? There's still an infinite amount of open space. It's just, in a relative sense, not as much open space as we had before. So can we fix that problem and not have this issue of infinite open space? So what's missing from our definition of open space risk? This definition doesn't tell us how to define O. And that's a big issue. If we don't know how to do that, we're not going to be able to estimate the risk appropriately. Actually, looking at this formulation, you are correct. The bottom is 1. I misinterpreted what you said before. Yes?
I'm a bit confused about, like in the training data set, you certainly just don't have any objects, right? So for example, in the take 10 digits and this data set,
Yes.
Let's say you have 1 to 5, but you don't have 6 to 10. You train on 1 to 5, 0 to 5.
Yep.
You apply to like 10 digits.
Yes.
Like what label you're gonna give to those like?
The ones that you don't know about, it should be a rejection label. Yeah, so this is similar if you've looked before at, say, like anomaly detection or outlier detection type algorithms. It's this kind of other class that they assign. Yeah, exactly. Okay, so to address this, we can introduce an abating process into the algorithm. This is just going to be some model-enforced decay of probability away from supporting evidence. So you can imagine a radial basis function perhaps fit around positive training data points. And that's a great function here because it does abate, right? It has a probabilistic decay away from the positive samples. And so when we have this, now we can have basically a probability of 0 once we've gotten too far from the training data. And that's exactly what we want. 5 minutes? OK, almost done. So we can get that with some different probabilistic modeling. So here we're going to fit a model to the tail of the positive side of a decision boundary. So what we can do is take our friend, the one class SVM, which I mentioned does not work very well because it tends to overfit its training data. But for this problem, that's not so bad because we're trying to just get an estimate in a rough sense of where in space that positive training data lives. And once we have that, we can apply over the scores that come from that classifier a Weibull fit to the match data. And that gives us a probabilistic sense of class association. And then we can use that as an initial stage for an algorithm to determine, am I close to the positive training data? If yes, then I'm going to apply some additional statistical models to figure out what the probability is of being associated with the positive class. So in this model, which we call compact abating probability, I have this thresholded region, which is defined by that calibrated one class SVM. When I have my MNIST setting, perhaps I have a detector for the digit 3. I have a point in space. If it falls in the cap thresholded region, great. We'll move on and do the classification. If I'm too far away in space because I have something that is not the digit 3, I'm just going to reject that. It's beyond the support of the training data. And so, as I mentioned, the one class model is pretty weak. So we can move on to a more powerful binary model where we have a dual tail fitting. And again, we invoke the statistical extreme value theory here because in many cases we're dealing with extrema around decision boundaries. So this tends to be an appropriate model to use. We can do a Weibull fit to the match data, and we can do a reverse Weibull fit to the non-match data, giving us then a very strong confidence indication of class association. And when we do this, we get results that are indeed much better than what we achieved before with the one versus set machine. So here is the WSVM, which is the top curve. Again, on that same exact object recognition task I introduced earlier. And then the one versus set machine, which we described before, is the brown curve there. And on the x-axis, we're increasing problem openness. So notice these are a whole bunch of different approaches that we've adjusted in some way to deal with open set recognition. And some are more effective than others. Some are, again, very basic. We just added a threshold to one versus all binary RBF SVM. Others make some use of this extreme value theory modeling in interesting ways. But this WSVM model tends to be the best. All right, one more thing, because I know I have about 30 seconds left. We have another model which extends this process further, doing incremental learning. So if I've identified something new, a novel, unknown in the world, and I want to incorporate that back into my model because I think it's interesting and I want to identify it in the future, what do I do? Well, we need a new model then that can incorporate that basically in real time and not be extremely expensive where I have to basically bootstrap this whole thing again and retrain. So we have a new model which we call the extreme value machine, which uses the extreme value statistics inherently. So we dispense with all of the post-hoc score analysis, and we learn a decision machine which is kernel free, but is similar to a kernel method, but instead using margin distances which are defined by extreme value distributions. And this gives us a series of what we call extreme vectors instead of support vectors, which then define a decision boundary. And this is great because it's very, very efficient to train, and it supports this incremental learning. And it is also, again, probabilistically calibrated and lets us do the open set recognition. And so we've benchmarked this on some recent computer vision tasks for what is called open world recognition, where again, it's not just open set recognition. You have to incrementally learn some class. And so this is the state of the art for that particular problem in vision. All right, so that's it. I'm happy to take any other questions that are out there. Thank you. Thanks. Nope.
I have a very naive one.
Sure.
Could you show again the raccoon?
The raccoon, yes.
The raccoon.
I may have to.
How does the computer know that the question you ask is find the dogs and not find the mammals?
So that's a good question. We don't, right? Because when we train something like a support vector machine, you just have feature vectors and labels, right? And so you make this implicit assumption that the computer is going to figure out it's dog, not mammal. But you're right, this is close enough, right, to dogs where it's not a surprising mistake. So how do we solve that? There's a whole other area of computer vision called fine-grained recognition, which is trying to develop methods that do, say, hierarchical clustering, so you can make those fine-grained distinctions and categorize things that way. But this particular approach doesn't do that inherently. But that's a great question.
Okay, so let's thank Walter again.